So today we're going to go higher dimensional, not that higher, we'll stay with 2 dimensions more or less. And, but what I say for 2 dimensions will be easy to generalize to higher dimensions. The topic of today is going to be linear maps. Is really kind of the next step in terms of the simplest. We're just going up, you know, you're looking at the simplest examples. And I'm not going to give very detailed proofs, but everything I say, all the details are in the notes. So you should, you know, so I consider that part of this course is not just what I say on the board, but what I refer to. If I give a proof or a, you know, sketch of a proof, then you should actually be able to fill in all the details yourself. Okay. So, what is a linear map? So the simplest, so linear map basically means a matrix, right? So the space of all linear maps is the space of all matrices, seen as maps from R2 to R2, right? So you have here A of xy is equal to x plus by cx plus dy. So let's look first of all at the simplest possible case of this, in which we have a diagonal matrix this means that A of xy is equal to A. In fact, let me write it more in normal. This is the usual notation we use in, with matrices, but let me write it more with the notation we use for maps, which is simply that we have 2 coordinates, and this would give lambda 1 x, lambda 2 y. Right? This is this diagonal linear. So this is particularly easy to study, and of course it depends on lambda 1 and lambda 2, but the key observation is that if you restrict yourself to the axis, then these are just exactly the one-dimensional maps that we studied before, right? We looked at all the various cases. So if you take y equals 0, right, then y equals 0, which is the x-axis. So for y equals 0, for example, so a x 0 is equal to lambda 1 x 0. This means that the x-axis is invariant. It maps to itself. The y-axis is also invariant. This is the x-axis, this is the y-axis. So initially in our study, we can just look at the dynamics on each axis. And what is the dynamics on each axis? The dynamics is just the linear dynamics that depends on this lambda 1, right? So what are the various possibilities? You remember all the options, right? We kind of looked at various cases, lambda 1 between 0 and 1, lambda 1 bigger than 1, lambda 1 equals 1, all these cases, right? And the same thing for on the y-axis. So let's look at some different possibilities here when we combine. So let's suppose, for example, in this case first that lambda 1 is between 0 and 1, and lambda 2, what should we choose? Also between 0 and 1? No, let's put bigger than 1. Okay, we will look at all the different combinations. So what happens? Well, if you take a point here, let's choose a point, say 1, 1. This is x0, this is y0, right? Then you see that the image of this point just follows independently the 2 coordinates, right? So we know that if lambda 1, maybe I should have chosen, well, since lambda 1 is between 0 and 1, that means that x1 is close, is converging to 0, right? But lambda 2 is bigger than 1, so y0 is increasing, right? So here is x1, here is y1, multiplied by lambda 1, this is multiplied by lambda 2, and the point is here, right? and then you have some point here x2, and y2 is here, okay? And if you think about it, it's easy to see, and then you can go backwards. This is invertible, right? So if you take the inverse, then it is just multiplication by 1 over lambda 1 here, and 1 over lambda 2 here. So you can see that x minus 1 would be something here, y minus 1 would be something here. And you see that, in fact, all of these points, they lie on a curve which goes like this. Which is actually geometrically a hyperbola. And this will be actually the origin of hyperbolic that we said before. Okay? So the curve is not the orbit, but the orbit lies on the curve. Right? So if you take a different point on this curve, it turns out that also the orbit will lie on this curve. So this curve is invariant. You can check it quite easily geometrically. You can find the formula even for these curves in terms of lambda 1 and lambda 2. Right? So if you take another point here, it will lie on a different curve here. Also here, if you take the points, we'll have some curve like this, some curve like this, some curve like this. It's quite easy to see. So here we are assuming that we have a contraction in the horizontal direction and expansion in the vertical direction. So points are moving in some sense in this direction, if you want. Sorry. Yes, in this direction. What about lambda 1 in 0, 1 and lambda 2 also in 0, 1? Lambda 1, and let's suppose lambda 1 less than lambda 2 less than 1.
It will converge to the origin?
So it has to converge to the origin, that's right, because in both directions it converges to the origin, right? So what do the curves look like? So if you take a point in here, you take a point x0, y0, so this is x0, y0. So the x coordinate will be converging to the origin, the y coordinate will be converging to the origin. So what would be the shape of the curve that it lies on? Will it be straight line? Well, not necessarily, because this will be lambda 1 x0, and this will be lambda 2 x0. In fact, in this case, it will be a little bit different. So this will be lambda 1 x0, and here will be lambda 2 y0. So they will not be the same. If lambda 1 was equal to lambda 2, then they would both go by the scale by the same proportion, and then we would get that these points lie on the line. But because lambda 1 is different from lambda 2, then the line looks a bit different. And what's happening is that lambda 1 is closer to 0, so lambda 1 is a stronger contraction, right? So the proportion, it proportionally comes closer in the direction, in the horizontal direction, right? So it turns out that the curve, again, you can kind of check, is tangent. It will look something like this. It will come in like this. Maybe not exactly like that. Something like this. It is actually tangent here. Because intuitive. You don't need intuition because, as I said, if you do a little bit, you can calculate the actual shape of the curve fairly easily. But
would be y to the x to the lambda over lambda 2, lambda 1 over lambda 2.
Exactly. Yeah, exactly. Probably something like that. Yes. But so the key point is that this comes in like this, right? So all the curves will come in tangent to the vertical because the horizontal is shrinking fastest, right? So these points, they move faster in the horizontal than in the vertical, but they're all moving. And so here you also get something like this, here something like this. So I put two arrows to show that we're contracting. It's a stronger contraction in the horizontal direction. Well, these are pretty much really the only two cases, right? All the other cases are more or less variations. If lambda one, if lambda 1 and lambda 2 are both bigger than 1, then you get exactly the same picture, but just points are moving away. Right? Again, depending on which one is bigger, the curve will come in this way, or it can come in this way. Wait, let me just draw this other here. If lambda 2 was greater than lambda 1 was greater than 1, then you would get just similar curves that coming down like this. Because here you have a stronger contraction in this direction. So the other things that can happen are that one of them is equal to 1, right? So there are some kind of slightly degenerate situations, like suppose that lambda 1 is less than lambda 2 and lambda 2 is equal to 1. Then what happens in that case? So since lambda 2 is...
Do like this.
So since lambda 2 is equal to 1, then in the vertical direction is the identity. Right? In the vertical direction is just y goes to y. In the vertical direction is the identity. So that means that that if you look at a point here, it will contract by lambda 1 in the horizontal, but it stays on the same vertical level. So all the curves are like this. And here you have contraction towards 0, right? So these are all fixed points. Every point on the y-axis is a fixed point, and everything contracts like this, okay? This we would say, I will give the general definition because this is just for diagonal matrices. Okay, for the moment we're studying this. We will generalize them in a second, but this is the fundamental picture. And again, you will see that the problem, just like in the one-dimensional case, remember the derivative equals 1 was kind of a problematic case. Also in this case, we will define all of these cases are called hyperbolic, coming from this picture, but by extension also in this case, as long as both of these are the two eigenvalues of the matrix here, they're different from 1, and then everything happens. If one of them is equal to 1, then you get some kind of degenerate situation like this. So remember, there's other possibilities that can happen. You may have, for example, both of them being of absolute value less than 1, but one of them would be negative. What happens if one of them is negative?
It do something like this, like a
Come on, guys, think actually. Yeah,
Does it make
it just jumps.
Yeah,
The picture is exactly the same, but it flips over in one direction. The picture is the same because the absolute values of these curves, this family of invariant curves still exists, except that this curve after one iterate maps symmetrically to this curve. So this point, instead of mapping here, it maps to the symmetric point on this side. and then it maps to a symmetric point on this side, then it maps, so it's still converging to 0, but it is flipping sides. This is if lambda 1 is negative. Right, so it's kind of orientation reversing on that side. But the picture is exactly the same. If both of them are negative, then it flips like this. Right, because it flips on this way and it flips on this way. So this point moves to the corresponding point here, and here, and here, and here. It's just negative. Each coordinate goes negative. Okay? And the same thing here. Here, if one of them is between 0 and 1, you have a contraction, you have an expansion. But if one of them is negative, then you just flip. So instead of this point moving along this curve here, it will still move, but instead of moving to here, it will move to the corresponding point here, then here, then here, then here, then here. And it just flips on both sides. Okay? So if here we have a third kind of point, right? In this case, if both of these have absolute value less than 1, then this is an attracting fixed point. The origin is always a fixed point, it's an attracting fixed point, right? If both of them are bigger than 1, you will get the same picture, but this will be a repelling fixed point because points will be moving away, but exactly along the same lines, right? So we have attracting fixed points, we have repelling fixed points, and we have this new kind of fixed point, which is neither attracting nor repelling. It's called a saddle fixed point. Sometimes it's called a saddle. Saddle is what you ride on a horse, right? You put on a horse and you ride on the saddle. It kind of has this kind of shape that in two directions is going up, in the other direction is going down. I cannot draw it. But there's also a reason, because this sometimes comes from certain manifolds, some geometry that has a kind of saddle structure is kind of similar to this. But anyway, this is what it's called, saddle fixed point. Okay, so before we go forward to more general linear maps, let's continue with these ones and talk about the problem of topological conjugacy, which is our focus, right? The classification. So, are these two topologically conjugate? Can these two be topologically conjugate?
No.
Why
This
not?
has a certain point, this doesn't have a certain point.
And so?
It should be that if this has a converging attraction point, if there were, there should be an attraction.
Exactly, the same issue we've talked about, right? That the omega limits, all these points, the omega limit is the origin, okay? Whereas these points, the only points that have the omega limit in the origin are the points on the x-axis, they converge to 0. All other points, they go to infinity. Okay? So topological conjugacy has to map omega limits to omega limits of corresponding points, so it cannot be. Okay? What about these two? What about two different ones if we take two different linear maps? Both of them have attracting fixed points, and both of them, but they have different values of lambda 1 and lambda 2. What do you think? Josh?
I think they should be topologically conjugate.
Why?
Because they all have the omega limit is the origin. So
Yes, but that is a, yeah. It's not a sufficient condition, it's a necessary condition, right? But
and they should have the same. Since they only they have just single attracting fixed point.
yes.
So meaning they have the same number of attracting fixed points.
Yes, but then again, that's necessary, not a sufficient condition, right? In the sense that if two systems don't have the same number of fixed points, they cannot be. But it's not enough. For example, yes, so you're right. You pointed out two conditions that are necessary, that they just have two same fixed points, and both of these are attracting. But does this guarantee that they're topologically conjugate?
Then we talk about the bijection.
So the question is, can we construct a conjugacy? So why don't you tell us how to construct this conjugacy?
Okay. Do we use the fundamental domain?
Yeah.
Since they have only single fixed points, we we construct an open neighborhood around the fixed point for this and the other. And then we take H naught, which is the bijection between the fundamental domain of this and the fundamental domain of this.
So what's your suggestion for the fundamental domain?
Okay, so that's open neighborhood around 0. Such that for any point, every point enters the neighborhood once.
But they don't, because these points, they stay inside forever.
We need to take a strip.
We need to take a strip. That's right. So, actually in
But
this...
didn't we just flip the coordinates? We send xy to yx. Because these two situations look like more or less symmetrical.
Yes, but suppose lambda 1 and lambda 2 are different. I mean, even if they both look like this, we have the same problem. We also want, in that case, to prove conjugacy.
Yeah, but we can multiply by a some constant in different constant in both coordinates, so that to accommodate for this, to make the lambda 1, lambda 2, and vice versa.
That becomes a different map. Then.
No, we need to construct a homomorphism
between the two.
Yeah.
Okay, so let me say that this is the right strategy. In fact, we're going to use this strategy in the slightly more complicated way in the second half of the lecture, right? But in this particular case, there's an easier way. This would work. You'd need to take this and the image of this, and take the disk between them. Okay? But in this particular case, there's several different ways we can do it, and the easiest one is just to find the conjugacy first on each coordinate. So we're looking for a homeomorphism of R2 to R2, right? But we already know how to do it in one dimension, right? So we already know that here, this is a one-dimensional linear map which is contracting, and this one also, right? So how did we construct, let's call this homeomorphism on the x-axis. So how do we construct the conjugacy between the dynamics on the x-axis here and on the x-axis there? That we can do exactly by the method of fundamental domains that we did before, right? Because in one, for the interval diffeomorphism is the same. If you take a point here, and you take its image here, and you take this region here, this is a fundamental domain by the same arguments we used before, right? Because any point is moving in forward time to here, in backward time to there. So any point, its orbit in future or past orbit will spend one literate here, and then we can do the same here. And we can construct a fundamental domain, so we can construct a homeomorphism between the dynamics restricted to the horizontal axis. And in the same way, we can construct a homeomorphism of the dynamics restricted to the y-axis, because this also is contracting, this is contracting, so we take some fundamental domain here, some fundamental domain here, and we construct the homomorphism there. And then we just take h. You can check that if you take h of xy equals hx of x and hy of y. So you construct a homomorphism between the two, whose two components are just given by this. And that gives a homomorphism and a conjugacy. Okay, check. H is a topological conjugacy.
Why we are always looking to
You mean why should not lambda 1 equals lambda 2? Yes, in this particular case it doesn't make a difference. It can work exactly just fine in this case, yes. It will be a bit more difficult now when we look at the general case. If the two eigenvalues are the same, it's a bit difficult. But in this case, yes, if lambda 1 was equal to lambda 2, if lambda 1 was equal to lambda 2, then you would get straight lines, as we said. Okay, but you can still do exactly the same argument for the conjugacy. And the same argument works if you've got two saddle fixed points, right? Wait, so of course this argument does not work if the signs of these are not right? If one of these has negative signs, so we did not really talk about topological conjugacy in this case when you have orientation reversing, but if one of them is negative, then what happens is that the image of this fundamental domain, instead of being here, is symmetrically here, and then it flips like this. Okay, so in that case you will need to take as a fundamental domain, you will need to take two regions here, symmetric regions, and then you know that every orbit on the whole real line, because when lambda 1 is positive, then you're constructing this conjugacy by looking just at all the orbits that are on the positive side of the x-axis and then on the negative side of the x-axis. So in fact, in both cases, you need to take two fundamental domains. Sorry, I did not emphasize that, right? Of course, in this case, this fundamental domain is just a fundamental domain for the positive real axis. So when you construct this conjugacy, you construct it on the positive real axis like this. Then you need to do the same thing on the negative real axis, right? So in fact, the fundamental domain for the linear map is given by two connected components, one on the positive real axis and one on the negative real axis.
But can you take x to f2x?
Sorry?
One region from x to f2x. Double integer.
If it's negative, if the eigenvalue is negative, yes, if the eigenvalue is negative, it's just that to construct the conjugacy, you need them both to be negative, right? Otherwise, it's not going to work. If this one is negative and this one is positive, then it's not going to work, because you would, where would you map? Where would this homomorphism map the positive real axis? It cannot. If you take the positive real axis and this homomorphism maps the positive real axis to the positive real axis, then this will not give you a conjugacy, because in one case the image of this point here will stay on the positive real axis. In this case, the orbit will stay on the positive real axis, whereas in this case the orbit will flip each time. Okay, sorry, maybe I went a little bit too fast with this. Let me make this comment. So, how should I say? So, we can construct topological conjugacy by method of fundamental domains. Okay? But just notice that if you have x goes to lambda, if x goes to lambda x, and well, I've got if you have two linear maps, two one-dimensional linear maps, x goes to yx, lambda x, and x prime goes to lambda prime x prime. I'm using two coordinates here, x and x prime. Yeah. If lambda, let's use this example here, lambda prime less than 0, less than lambda less than 1. Okay, so we have two linear maps. Both of them have contracting fixed points. Okay, but one of them is negative, so in one case this flips. Okay, so let's try to construct the conjugacy that we want to construct. Okay, if in both cases the fundamental domain for this will be formed by two regions, right? Okay, so we take a point X and we take its image here, and then we take some other point X here and we take its image here. Okay. Here we take a point X prime, and then as you say we could take F2 of X. But F2 of X, then how are you going to, so here we could take, it's true that F2 of X would be here, F2, G2, well, okay, this is F and this is G, but the linear maps, so this is F2, G2 of X prime. So how are we going to construct the conjugacy?
We map both of the intervals to this bigger one.
Off the top of my head, I'm not sure that I can see how to prove to you that you cannot do it this way, but
time is not same anyway, maybe. Because this is G2, this is so time.
yeah.
Why is G2? I don't think G2 is a fundamental.
Yeah.
Yes, because of X dash itself, it will be have two images.
No, because the first image is on this side, right? That's the point. This is flipping around. So this is F of X prime, and this is G of X prime, and this is G2 of X prime. So how do I convince you that you cannot do this? I think it's simply because you cannot have a homeomorphism. I mean, we're trying to construct a homeomorphism, H, right? And which preserves the dynamics. So this homeomorphism needs to map this fundamental domain. This homeomorphism needs to map the real line to the real line. It needs to map 0 to 0. And since it's a homeomorphism, it needs to be monotone. So it needs to be either orientation preserving or orientation reversing. And it needs to map orbits to orbits. I think it's as simple as that. So if you take a point here on the positive real axis, it's going to stay on the positive real axis, okay? That means that H must map the positive real axis. This means that it cannot be, right? Because if this is a homeomorphism and it maps 0 to 0, then this positive real axis must map either to the positive real axis or to the negative real axis. There's no other options. So it cannot happen. Cannot construct a conjugacy if one of them is orientation preserving and one of them is orientation reversing. I'm not sure how to give a good conclusive argument. You're convinced that you cannot do it? How would you construct the conjugacy? What would we do? We map this domain to what? To this domain? There's just a topological obstruction to that, which at the moment I'm not able to say in the ideal way. So the conclusion, I think you can try to do this, but you can convince yourself.
I think just if we take this X and the f of X, if we take a point inside the interval and a point outside the interval and they are very close to each other. When we map, the point inside the interval will be mapped to between X dash and G squared of X dash. So it will be on the right of the zero. right? But the point outside will be mapped to the negative one.
Yeah,
So
yeah.
it can't be
It
continuous.
cannot be, yes. I think that's a good argument. You take 2 points nearby. This is supposed to be a continuous map. This point will map to some point in wherever you want to map it in this fundamental domain. This point needs to be mapped close by, but instead by the dynamics, here this point, whatever it is mapped to this side, so this map would have to be mapped to this side at the same time. So you just cannot do that. Okay. Yes, sorry, I forgot that we hadn't, because we did it for interval diffeomorphism, we hadn't looked at the case where you're really trying to conjugate two linear maps where one is orientation preserving and one is orientation reversing.
I think the H can be constructed explicitly in this case, in terms of matrices.
Yes, it can, because it's just in this case you can because these fundamental domains that you can take 1 and then this is just lambda 1. You can put numbers to all of this. Yes.
Even if lambda 1 and lambda 2 are not even if we are mapping different lambdas.
Yes, that's what I mean. But because this dynamics is very explicit in each coordinate, then this is the conjugacy between these two linear maps, and it's again something like probably lambda 1 over lambda 2 or something like that.
It will be a matrix. I think it makes sense in terms of matrices because when we try to construct the matrix, if one of them is positive, then you have to take a square root. If one of them is positive and one of them is negative, then the square root would be an imaginary number. So it makes sense of this in this context.
Okay, maybe you can try to derive these explicit formulas. Maybe, yeah.
So I'm a little bit confused. Here we say that we have this explicit topological conjugacy.
Not so explicit. I'm not emphasizing this explicit.
Yeah,
I don't know how
but
explicit you can
we
make
show
it.
that there is someone,
But-
this candidate.
Yes. No. This is explicit in the sense that it's explicit in terms of the one-dimensional conjugacy between the axes. It's just this.
Yes, but here we are saying that we can't find
If one of them is negative and one of them is positive, right?
Okay.
This is what I was emphasizing. Yes, because I forgot to say. So because I'm trying to say that the key that these are more or less all the cases, right? If lambda 1 and lambda 2 are both different from 0, if A is hyperbolic and lambda 1 and lambda 2, sorry, different from 1, okay, then basically these are all the cases that can happen. If they're different from 1, then that means that they're either contracting or they're expanding, and they're either positive or negative. So these are the only possibilities. So here, this is the case where one of them is contracting, one of them is expanding. This is the case where both of them are contracting. The case where both of them are expanding is exactly the same picture. Okay? So what I'm saying is that in all these cases, what they have in common for the moment is that the horizontal and vertical axes are invariant in all these cases. And the horizontal and vertical axes, they're just one dimension. The linear maps restricted to these are just one-dimensional linear maps, and therefore you can construct the conjugacy the way we do it for one-dimensional linear maps. So whenever, basically, the conclusion is, I'm going to write a more general theorem for more general linear maps, but in this particular case of diagonal matrices, it's easy to verify that they're topologically conjugate if either both of them are have absolute value between attracting. If both of them have attracting fixed points and the signs of the corresponding eigenvalues are the same. This is the point I was trying to make here, right? So contracting, so the origin, so the linear map has a contracting fixed point, if the absolute value of both eigenvalues is less than 1. Okay? But that includes the possibilities that one or both of them may be negative. right? So if you have two linear maps, both of which have contracting fixed points, and the signs of these correspond, then you can, then they're topologically conjugate. If the signs do not correspond, if one of them has two positive eigenvalues and the other one has one negative and one positive, then you cannot do that. You cannot, they're not topologically conjugate. And similarly for the saddle. For the saddle fixed point, one is positive, one is negative, but if the signs do not correspond, then it's not, they're not topologically conjugate.
You mean if both of them are between, if we have two systems and the lambdas of the first are between 0 and 1 and the same as the second, they are topologically invariant, right?
Topologically conjugate.
Yes.
As long as they have the same signs. Right? If you have two saddle fixed points, because it's the same argument as before, you need to take the conjugacy on the horizontal axis and the conjugacy on the vertical axis. And if one of them has lambda 2 bigger than 1 positive, and the other one has lambda 2 less than -1, so it's still expanding, repelling in this direction, but it flips, then you cannot construct the conjugacy between them. So they need to have corresponding signs. Yeah, sorry, maybe I tried to go a little bit too fast and I should have done a little bit more systematically built up these cases. But I think when you go through it again, you see those are all the possibilities, either bigger than 1, less than 1 in absolute value, positive or negative, and you can easily see by this construction and this observation that which ones you can are topologically conjugate and which ones are not. So what about matrices that are not diagonal? So let's go with a little bit more general, and let's suppose A B, C, D has, so as you know from linear algebra, A has always two eigenvalues with multiplicity, right? And let's suppose for the moment that A has two distinct, these eigenvalues can be real or complex, distinct real eigenvalues, lambda 1 and lambda 2.
So matrix is diagonalizable, and we can make diagonal form, and we can.
So what is this diagonalization process? So first of all, so eigenvalues correspond to eigenspaces, right? And what is the
Eigenspace, it means that eigenvalues or the space of eigenvalues.
So what is the property of so the eigenspaces are two subspaces, right? So this is the eigenspace E1, and this is the eigenspace E2. And what is if you take a vector V1 in E1, then what is AV1?
Lambda 1.
Exactly. Lambda 1 V1, right? And if you take a vector V2 in E2, then AV2 is equal to lambda 2 V2. So where does the vector lambda 1 V1 lie? So the V1 lies in E1, right? So this is a point here. In linear algebra we think of this as a vector, but this is just a point here. So where is lambda 1 V1? It's also inside the subspace, right? So the subspaces are invariant by the linear map. That's what this property says. Right? So this here, let's take a point x, and this is x0, x1. This is equal to lambda 1 x0, right? And then well, we don't know what depending on what lambda 1 is, we have inside the subspace, we simply have the one-dimensional linear map lambda 1 v1. Okay, so inside the subspace, we just have a one-dimensional linear map. And again, the dynamics, now forget about the fact that this is not horizontal, it doesn't really matter, this is just a subspace, and we have exactly all the analysis that we've done before, exactly the same. And the same for the other one. Right? So what are the possibilities here? Again, we have all the exact same possibilities. So let's suppose, again, for simplicity, let's look at the first case. Let's suppose here that lambda 1, 0 less than lambda 1, less than 1, lambda 2. So what is the dynamics here? You know you can use these, you can draw coordinates here. So you can write a point, let me write it like this. You can write a point in these coordinates. This is x0, y0, right? And then x0 maps by lambda 1, so it maps here. Y0 maps by lambda 2, so it maps here. Okay, maybe I should have drawn them small, closer to here. Okay, x0, y0, and then x1 maps to here, y0 maps up to here, so you get a point here, and then x1 maps here, and y, so this is x1, y1, x2, y2, okay, and what you get is that you get, again, some kind of, they lie on some curve like this. These points. Right? So you get a very similar picture, and you get all these curves like this. So here you have that this is contracting in this direction, it's expanding in this direction, so all the points are moving. This is moving like this, and this here, so this is expanding. These are like this. This is just a heuristic, this is just a picture, you know, that I've sketched. I haven't proved that it's like this. How do we kind of formally justify this picture? Well, as you correctly said, the matrix is diagonalizable. What does it mean that it's diagonalizable?
They are conjugate.
They're conjugate. What do we mean by they're conjugate? Sorry?
Conjugate with the diagonal.
But what does conjugate mean?
We change the basis to make the representation of the linear transformation of diagonal matrix.
Okay, what does it mean that we're changing the basis? What does this conjugacy look like? So let's call this matrix here is, so here we had our matrix A, which was equal to, sorry, maybe I should have used B here to distinguish it, sorry. B here. So our matrix A was lambda 1, 0, 0, lambda 2. Let's suppose we have the same eigenvalues here. So what does it mean that this is conjugate? It means that we can write B
DA
There is some C, C matrix, C minus.
there's a matrix C. Are we all okay with this apart from linear algebra? You okay with this?
Yeah.
You know this? Okay. So it's diagonalizable, means we can conjugate it. So how does this fit with what we, you know, this word conjugacy that you use? Is it the same conjugacy that we have dynamically, or is it a different conjugacy? It's the same conjugacy, right? It really means these as maps. So in this matrix multiplication is really composition, is the same thing. The matrix multiplication is the composition of these matrices as linear maps, right? So here we can we can write it as, now I can't remember what notation, but you can multiply both sides by c minus 1, and you get c minus 1 b is equal to ac, which is a little bit more similar to the conjugacy. Sorry?
CB.
Sorry, CB, yes. CB equals AC, okay, which is the same way, which means really as linear maps, what does it mean? That if you take a vector, we take a vector here, and we apply the, so here we have our map. In fact, if you don't mind, let me call it H. So, let me call it H because this is the notation we've been using for conjugacies. Sorry, I keep changing here. Okay, so let me call this H, big H, to show that it's a linear map. Okay, so it means that if you take a vector here and you apply H, right, and then you apply this linear map, you get the same thing as if you apply this linear map and then you apply H. Right, so it's exactly the same conjugacy. It's really a dynamical conjugacy. So is this a topological conjugacy?
Yes.
Is it a C1 conjugacy?
Yes.
Yeah, it is the best possible conjugacy. It's C1, C infinity analytic linear. It's like you cannot get better than linear. Right? So in some sense it's like the most strongest possible conjugacy you can have. Okay, they're linearly conjugate. Okay, so these two maps are linearly conjugate. So AB, so when we say that it's diagonalizable, what we mean that B is linearly conjugate to A in diagonal form, like this, linearly conjugate. Yes.
So what does it mean for a matrix to be C1 or C2?
No, a matrix is a linear map which has as much regularity as anything. I mean, it's as a linear map, it's differentiable. If you think of it just as a map from R2 to R2, then it is differentiable to any order. I mean, it's just it's differentiable as a linear map.
But what does it mean to be differentiable?
The same as it means for any two-dimensional linear map to be differentiable, that the partial derivatives exist. It's not usually thought of as being, you don't think of it as being differentiable, it's kind of trivially differentiable. The derivative of the linear map is itself. If you have a map, what does it mean for any map f from R2 to R2 to be differentiable, to be C1?
I don't know.
And then it is this.
Oh, you don't know this. But you know what it means for one-dimensional map to be
Yes. And vector value is okay, but not from R2.
From R2 to R2 just means that the partial derivatives exist, so you need to revise your kind of calculus a little bit. This is just, this is a map x, y, right? And this you can write as two components, f1 of xy and f2 of xy, because this has two coordinates. So you write any map from R2 to R2, you write it as a map where you need to define the image of this map, the first coordinate and the second coordinate. So you have two functions. Each one of these takes this point and it tells you what the value of the first coordinate is, and this tells you what the value of the second coordinate is. Right? So each of these is now a map from R2 to R. Right? And as a map from R2 to R, you can take its partial derivative with respect to x, its partial derivative with respect to y, in this case, and if all four partial derivatives exist and are continuous, then the map is C1. That's the definition of C1 in higher dimension, with the partial derivatives. It's all like that. In any dimension, it's like that. Okay? So we cannot go into it, but do a little bit of review of that, of these definitions of derivative. But in some sense, a linear map is differentiable in the highest possible sense. Okay? Good. So, what are we going to conclude from this? So, we have that is this map now topologically conjugate? So, okay, so the question is now, So suppose A and B are two-dimensional linear maps with real distinct eigenvalues. Lambda 1A, lambda 2A, lambda 1B, and lambda 2B. So are these two linear maps topologically conjugate? When are these two linear maps topologically conjugate?
Hegemonies are same in this case. As a pair of hegemonies is same as pair of hegemonies.
So suppose,
So you got the question again?
yes, when are they topologically conjugate? Suppose, for example, that they both have, they both satisfy this condition. Okay, the same here, and lambda 1b less than 1. So suppose they're both saddle points. Okay, but they may look very different, right? So this one may have a saddle point, may look like this. And then this other one, the saddle point may look like this. So are these topologically conjugate?
Yes,
Why?
because there exist invertible matrix which conjugates to, well, I don't know if that exists, but we can say it exists. Oh, as you mentioned before, we can construct using
The axis.
exactly, rotate the axis,
The axis.
rotate and expand, contract.
Okay, so what we can do is we can use this observation we just made here and say, look, this one is linearly conjugate to this saddle, the diagonal saddle, the saddle in which the axes are horizontal and vertical. Here you have a linear conjugacy between these two. And the same here. Here you have a linear conjugacy with something that has also horizontal and vertical. Okay, so also it looks like this. But they have different and these eigenvalues are the same as these eigenvalues. So we diagonalize both of them. And these ones are conjugate because we just showed that they're conjugate. These ones we can conjugate exactly with the theorem of fundamental, with the technique of fundamental domains, right? So this gives, so this is some H1, H2, okay? And so we construct the conjugacy by composing these two linear conjugacies, and this conjugacy is between the diagonal version of the matrices. So notice that we've really taken care now of all the possibilities. I would like to do complex eigenvalues. We can take a little couple of minutes break, and then we look at the situation with complex eigenvalues, and then I will state a theorem that includes everything. But notice that we have really, as long as we have two distinct real eigenvalues, and as long as none of them have absolute value equal to 1, those are the degenerate cases, right? Then we have covered all the possibilities. So you can go and look at all the different cases. Here also you get a saddle point if you have this case. You have a contracting point if they're both less than 1 in absolute value, a repelling point, and all of them you can actually see that the picture is very similar. All you've done, as you said, is kind of change a little bit the direction of the eigenspaces. This is a special case. But using these two information, first, the fact that if you have two distinct real eigenvalues, then it's always linearly conjugate to the diagonal case. And then we've discussed all the possibilities of the conjugacies in the diagonal cases, so you reduce it to that category, right? So if two linear maps are both linearly conjugate to two diagonal forms which are topologically conjugate, then they're topologically conjugate themselves. If they're linearly conjugate to two linear maps which are not topologically conjugate, then they're not topologically conjugate themselves.
But what if we have a generic case when the eigenvalues coincide?
Yeah, so that means that it's not clear that you can diagonalize in the same way. Well, in general, if the two eigenvalues coincide, you are not sure if you have one eigenspace or two eigenspaces. So sometimes sometimes the eigenspaces might be distinct. So really, maybe I should say with two distinct eigenspaces.
Okay.
Yes. So as long as the eigenspaces are distinct, you can always do this.
Yes.
Or diagonalizable.
Yes.
Okay, as long as they're diagonalizable, it's okay. Yes. That's why I call it two distinct eigenvalues, because it's simpler. Yes. So some cases we haven't taken care of. You can say things in those cases also, but for simplicity, I just look at this basic case. Okay, let's just take a couple of minutes break, and then we'll do the complex. So let's continue with the case in which we have complex eigenvalues, right? So, which becomes a little bit more tricky, because as you know, so now let's suppose that A is equal to alpha beta minus beta alpha. This is the kind of normal form, the standard form when you have complex eigenvalues, and this corresponds to having eigenvalues lambda 1 and 2, which are equal to alpha plus or minus I beta. So what is the dynamics of this? You know what the dynamics is of this?
Just two eigenvalues.
Yes, but what is the dynamics of this? What does that... Take a point here. It's a spiral, right? So yes. So you can write it as multiplication by complex numbers. So you can write, I'm not actually going to do all this, but you can revise it if it's not familiar. But you can, so you can write this complex number as a polar coordinate. So like alpha plus alpha, how should we do it? So alpha minus I beta, we can write it as r e to the I theta in polar coordinates, right? And then it turns out magically that, or not so magically, that this is just multiplication by this, right? So if you write this point here also as, so if you write this as, if you write this point here in polar coordinates, which is much more suitable for this, then it turns out that A of R0 e to the I theta 0 is equal to multiplication by this. So R times R0 e to the I theta 0 plus theta. So this is just multiplication by this, and from this you can easily see what's going on. So of course this R is the modulus of these eigenvalues, right? So these eigenvalues are two eigenvalues on the complex plane. This is the unit circle, this is the complex plane. So if alpha minus I beta is in here, alpha plus or minus I beta, so this is alpha, and this is beta, right? So if alpha and beta, if this lies inside the unit circle, then R will be less than 1, right? So that when you multiply by R, you will be shrinking, right? So you will be adding an angle theta, and you will be shrinking from R0 to R0 plus R, and then you add theta again, and then you're shrinking again, and then you add theta again, and then you're shrinking again. Okay, and then you can see that what's happening is that you are moving along a spiral like this.
How do we know that the modulus is less than 1?
No, by assumption. The modulus the modulus of I depends on the eigenvalues. So this is the corresponding, this is what corresponds in the real case to the fact as to whether the eigenvalues are less than 1 or bigger than 1, right? In this case, alpha plus or minus I beta are either both of them inside the unit circle or both of them outside the unit circle, right? So if they're inside the unit circle, in the case where R is less than 1, R is less than 1, so if the modulus of alpha plus or minus I beta is less than 1, then we have this case here. And if the modulus of alpha plus or minus I beta is greater than 1, then we have like this. Points are moving outwards. Okay, so every orbit lies on such a spiral, which means that there's lots of spirals. Okay, wherever you start, you spiral in. On every point, so there's a family of spirals, all of them going in. Here there's a family of spirals going out. This is the picture. Now, what happens in general? So if we have AB is equal to ABCD, and suppose that in this case we have eigenvalues, we have the same thing, eigenvalues, lambda 1, lambda 2 equals alpha plus or minus I beta, okay? But this does not mean necessarily that it's in that form. Okay, but what can we say? We have the same property we have that there exists a linear conjugacy that brings it into
In
that
fact,
form.
if it is diagonalizable, I think up to a change of basis, it must be on the basis.
Yeah, I mean this is not usually called diagonalizable as far as I know, but maybe you can call it diagonalizable. Anyway, this if it's got complex eigenvalues, then there exists a linear conjugacy. So then B equals H minus 1 AB. Okay, so linearly conjugate to A equals alpha B minus beta alpha. This is in the notes. In the notes I've done actually all the conjugacy.
H minus 1.
Sorry, yes. H minus 1, H. Just the same as before. Okay. In the notes I've got you can write out explicitly the conjugation of this one. So how does this help us? This is very good. What does it look like, by the way? In general, what is it going to look like? Because you don't have these eigenspaces anymore, right? This is the main difference. You don't have eigenspaces. So what is, in general, if you have this situation where this is eigenvalues alpha plus or minus I beta, it is linearly conjugate to this. So what does it look like here? What do these curves map to under this linear conjugacy, this spiral? You know that?
I don't understand the question exactly.
What if I take a point here?
Uh-huh.
What does the orbit look like? So the orbit is going to be on a curve that is the linear map. Remember, what is this linear conjugacy? Linear conjugacy said that there's a linear map from R2 to R2 that maps orbits to orbits, right? Because it's just like our conjugacy. So it will map each of these spirals to some curve here. Okay, because it maps all the orbits to corresponding orbits. So what is the image of the spiral here? What does the spiral look like? It's not necessarily going to look just like that.
The image of 0?
The image of 0 is going to be 0. This has to be. It's a linear map. It maps fixed points to fixed points. Remember, I draw, in the case of real eigenvalues, remember I drew the difference is that in one case the two eigenspaces are orthogonal, in the other case they have an angle and it kind of squashes everything in some sense, or it stretches everything. The picture looks the same. Now, intuitively, what does a linear map do to a circle? What's the image of a circle under a linear map? You know? It's an ellipse, always. Okay, a circle is an ellipse. So this linear map H will map a circle to an ellipse. Okay? So roughly speaking, it will look something like this. The spiral will basically look something like this. Okay? We don't know exactly how it is, but this is how it is. The only difference between this and that is that in this case we have the spiral will be stretched in this way. So it still will be a spiral. The points will still have to move around, clearly just because of the topology of the spiral it moves around. So the points on the orbit will move along this spiral in this way. Okay, so again, our problem is that of topological conjugacy. The question is this map topologically conjugate to this map? So, some other spiral that has some different maps. And even more significantly, is this topologically conjugate? Wait. Is this topologically conjugate to this map where you have, so they must be both contracting, but remember, so in this general case, this contraction will have some curves. There will be something like this. So I didn't draw this, but this is the non-diagonal form of a contracting map. I'm sorry, this corresponds to the case in which this one is a stronger contraction in this direction. Okay, you recognize this? This is just a contracting, but when it's not in diagonal form. So, are these two conjugates, supposing that they're contracting in both cases? Are these two conjugate? Is this conjugate to this? What is conjugate? So in the complex eigenvalue, if these eigenvalues have norm less than 1, so again here 1, if these eigenvalues on the unit circle, this gives some problematic situations because R in this case will be equal to 1. So I'm always, I forgot to say it, I'm always looking at the so-called hyperbolic situation. So R equals to 1 corresponds to the lambda equals 1. 1 is always problematic in this kind of theory. Okay? So we assume either that R is less than 1 or that it's bigger than 1. In these two cases, we assume it's different from 1. And we would like to know what topological conjugacy class all these things belong to. Okay? So we're going to show, or I'm just going to sketch the proof, and then you can fill in the details, that
curious to know if we have two fixed points in R2. This never happens.
For the linear map, we cannot have two fixed points. Well, we can if it's complex eigenvalues with norm equal to 1, right? Or if it's, for example, the identity map, then every point is fixed. If this is equal to R equals to 1, then what is this? This is just a rotation.
Yeah, but in this case it could be degenerate, so
Yes. Apart from the degenerate, yeah. No.
I don't think it could happen with linear maps. So
No.
which kind of maps would?
We're going to look at many different kinds of maps. I cannot go too fast. We will look at maps that have, like the 10x mod 1 that we looked at in the first class.
No, I am looking for R2.
Oh no, or in R2 lots. We will see some maps. I mean, yeah. It's a good question to ask yourself, but let's stick with linear maps for the moment. So, so the first observation is that it is sufficient to consider maps in this standard form like this, right? Because all the other maps, they're linearly conjugate to this one, okay? So suppose we can show, so we're going to show, let me erase some stuff here. So let A be like this, and let A be like this, and let's suppose that alpha plus or minus I beta is not less than 1, so it's a attracting fixed point. And let's be lambda 1, 0, 0, lambda 2, okay? And let's suppose that both lambda 1 and lambda 2 are between 0 and 1, so this is also an attracting fixed point. So here we have lambda 1 is more contracting, lambda 2 is less contracting, so if it's more contracting, everything goes like this. Okay, and the same on this side. So we're going to show that these two are topologically conjugate. Okay? And this then basically covers most of the other cases, right? Because this shows by the linear conjugacy, and these are topologically conjugate, whichever one, as long as these are less than 1, and as long as this is less than 1, with no other conditions on this, right? So this all of a sudden covers basically it says that any two linear maps which have attracting fixed points, as long as in this case both of them need to be positive here, right, in this particular case, and then you can always use the linear conjugacy to reduce yourself to these situations to construct the linear conjugacy, to construct the topological conjugacy between the two maps. Okay, so we've reduced, using this linear conjugacy, we've reduced ourselves to having to consider only the normal forms of the two matrices, and now we're going to do the technique that you were talking about at the beginning, right? Because it's not at all obvious here how to construct the conjugacy between here and here, right? Because here, in the previous case, we used the conjugacy in each of the two one-dimensional coordinates, but here we don't have this splitting, right? But now we can do what we said before, which is, sorry, let me draw this a little bit better here without this. This kind of thing. Okay. Now we can indeed do this. So I can take unit circle here, and I can take the unit circle here. So I can take S1, which is the unit circle, and then I can take the image of S1. So where is the image of S1 going to be? The image of S1, all these points are moving inwards, right? So the image of S1 is going to be, the contraction is stronger here, so it's going to be something like this. Yes? Whereas here, it's going to be exactly a circle. It's just going to be another circle contracted by a factor R, and here therefore we have this disk. So this is S1, this is B of S1, the unit circle, and this here is A of S1. Sorry, the other way around. B of S1, this is A of S1. Okay, so here we have this disk here. So we have these two annuli, and we claim that each of these is a fundamental domain for the corresponding map. Why is this a fundamental domain for this map? Except for 0.
Because what? Everyone goes in for some initial condition?
Everyone comes in.
Backwards or forward?
Yes. So every point comes in along these curves, right? So you take a point on this curve, right? Its image is on this curve. Its image is on this curve. So if you look inside this curve, it's again just like a one-dimensional setting, right? And by definition, this point here is the image of this point here, right? And we have order-preserving map because it's just going in. So this one comes here, this one comes here, this one comes here. There's no way it can jump over. Okay, so it must fall in here, and once it falls in here, it must fall outside because this is defined as the image of this. Okay, and you can do that for every point. And if you start inside, then you go backwards, and the same thing must happen. Okay, and the same thing here. So here you take a point, and you see that the curve. Okay, so this point here is the image of this point here. And so it's the same thing. You take a point, you reach here, and there's no way it can jump all the way because the image of this is here. So if you're to the right of here, you must end to the right of here. And then if you're to the left of here, you must end to the left of here. And so you go inside. So it's two fundamental domains. And that's it. Everything else just follows by the abstract theory that we had before. We need to show that it's homeomorphism. Okay, again, that's something. So given two fundamental domains, so these are two fundamental domains. Okay, so we construct, so we have H0 again, right? We have H0 is a homeomorphism. H0 from this disk, let's call this disk D1, or this annulus, and this is D2. H0 from D1 to D2, homeomorphism. And then we construct H0 as before. So construct H as before, as in one-dimensional case. And then you show it's a homeomorphism also exactly in the same way as the one-dimensional case, right? You need to look at different cases. This is a composition of maps. This is a homeomorphism. The maps themselves are also homeomorphism. So if you take points that fall inside the interior of the domain, then it's easy to see that at those points, the composition of A to the tau times H0 times B to the minus tau it's continuous. You only need to worry a little bit about the boundary, right? But it's exactly the same thing as we did in the one-dimensional case with the boundaries. And then you need to worry about it at 0, because you define 0 differently. So H at 0 is equal to 0, but it's clearly, again, just like in the one-dimensional case, if you take a point very close to 0, it will take a very long time to get here, and then when you map it, you map it back a very long time, so it will be close to 0, so you show continuity at 0. Yeah.
Is this yes, this conjugacy linear?
No, this is not linear. No. This is a construction by fundamental domain. This is not going to be a linear conjugacy. But it gives you a topological conjugacy between two of these here, and therefore you can extend this topological conjugacy to more general maps that are not in diagonal form, that are not in the standard form here, using the fact that if you have these kind of eigenvalues distinct, then you can diagonalize it to this bilinear conjugacy. If you have these complex eigenvalues, it is linearly conjugate to something of this form, and then you use the topological conjugacy between these two to get a topological conjugacy between those, the original maps.
Can we have do we have a general theorem of something like, if we have two spaces such that at every space there is a point, and every other point in the space then converges to this absorbing point, then the two spaces must be topologically conjugate to each other?
You mean if both cases you have a globally attracting fixed
Yes,
point?
Exactly.
Yeah, I don't think I don't think this is true. In the next lecture, we're going to do something. We're going to address basically exactly that problem, and we're going to show in some cases if one of them is linear and the other one is nonlinear. In some cases, you can do this. But if you just take two spaces and the only thing you know is that they're globally attracting, they're not necessarily like this, because you're saying that because these are both globally attracting fixed points and they have conjugacy. But we're using the structure, you know. And for example, why did I have to go to these normal forms? Why can I not directly construct the conjugacy with this, using the fundamental domain argument? Why did I have to change this by using linear algebra to linearly conjugate to this? Why can I not do it directly here?
Because fundamental domain is more strange.
Yeah, because it's not that easy to construct a fundamental domain. If you take a circle here, what is the image of this circle? It generally will not be contained inside itself. It will be something like this. It will not map inside itself. So it's not obvious how to construct a fundamental domain here. So that's why the big advantage there is that the distance from the origin of the points is monotonically decreasing. You see, these points here, they're not monotonically. You take a point and it is coming closer, but then it goes further away. So in fact, I think a very interesting remark that sometimes is missed, the fact that in linear, I did not maybe emphasize this very much, but one of the consequences of this is that if you have a linear map with two eigenvalues, both of them less than 1, then the fixed point is attracting. Right? I'm not sure if this is something that is really mentioned within the context of linear algebra, but within the context of dynamics, this basically follows from this. Because if you have, in general, you do not see, or this, if you have this less than 1, then this attracting fixed point. If you didn't know that, right, and you just look at this map here, and you don't know about these spirals, you just take a point and you try to follow the orbit of the point, it's not at all obvious that this is actually converging, because it might be very squished, so it might actually move here. So you might actually think that maybe this is actually, this is a hyperbolic point, because maybe this point looks like it's doing like this. It's not that obvious to actually look at a linear map without this linear algebra and this dynamical system theory behind it, and know just because you have these eigenvalues have norm less than 1, that is necessarily contracting fixed point. Okay, just want 2 more minutes because I really want to finish this section, and I won't say much about it, but I think you can do this. So the structural stability. Okay, so remember the structural stability is the notion is that you perturb something a little bit, and you want to know if it remains in the topological conjugacy class. So the natural space, in the case of interval diffeomorphism, we define the space of C0 metric, the C1 metric. The natural setting for linear maps is within the space of linear maps. Okay, so you want to take a linear map and you want to perturb it. You can also perturb it in the C1 metric, in the C2 metric. In 2 dimensions you can define that, but a natural thing is to stay within the world of linear maps. So you stay within the world of linear maps and you perturb it a little bit. Okay, so my question to you now, maybe I will just leave it as a question, is putting all this together, you can basically say what is the space of linear maps. So every linear map is of the form ABCD, right? So the space L R2, the space of linear maps on R2 is parameterized by these 4 parameters. So it is R4, okay? Because you can change the space of linear maps you get just by taking all possible ABCDs, and you get different linear maps, okay? So there's a natural topology on the space of all linear maps, which is just a Euclidean metric on R4. Okay, so you have R4, and you fix a point in R4, and that gives you a linear map because it gives you 4 coordinates, right? So A, B, C, D is a point in R4. And so you want to take another point that is very close to A, B, C, D, and you say, okay, that linear map, is it topologically conjugate to my original linear map? Okay, so I will leave it for you to think about a little bit, but you have all the tools to do that. Okay, and the result is really that every hyperbolic linear map is structurally stable. Okay, basically because the eigenvalues depend continuously on these coefficients, right? So if you change A, B, C, or D just a little bit, you will change the eigenvalues just a little bit, right? And we've just shown that as long as the eigenvalues are strictly between 0 and 1, then if you change these a little bit, then the new eigenvalues will also be between 0 and 1. Okay? And the same if they're bigger than 1, the same if they're complex. If they're complex, they still depends continuously. So all the cases we've considered in which they are different than norm 1. Norm 1 are also always these degenerate cases. Then all of these are structurally stable because we've just shown you change this a little bit. They have the same eigenvalues, and therefore by this construction we just did, they're all also topologically conjugate. Okay? Within the space of linear maps. Okay, so that finishes, and you can easily, if you know the linear algebra of linear maps, you know that when you have higher dimension, basically it always boils down to direct product of 2-dimensional, 1 or 2-dimensional spaces, essentially, most of the time. Okay, thank you very much.